Hey, welcome back. In this video, we're going to talk about double integrals in polar coordinates. What I first want to do to start this conversation is motivate the use of polar coordinates in double integrals in calculating volume or an area as we did in rectangular coordinates with this example right here. So what we have is we're being asked to find the volume of the solid bound by the paraboloid z equals 25 minus x squared minus y squared and the xy plane. The first thing that I would do is I would want to see what is the region on the xy plane, which we would integrate over, described by this paraboloid right here. And we can do that by simply setting z equal to 0. So if we set z equal to 0 here, we'll get 0 equals 25 minus x squared minus y squared, and then adding x squared and y squared over here, I'll get x squared plus y squared equals 25. So first and foremost, and we can confirm this with a visual right here, is that the trace on the xy plane of this paraboloid is this circle of radius 5. And what you'll find, and you should expect this from previous experiences, is that if you're trying to work with circular objects, it's much easier to use polar coordinates than it is rectangular, but I want to take a few steps in calculating this double integral, the volume described here, using rectangular coordinates. I'm not going to go all the way. All I'm going to do is far enough where I'm sure I can motivate, hey, there must be an easier way of doing this, and that easier way is doing a double integral in polar coordinates. So first and foremost, the region here on the xy plane is not rectangular, so we're going to need to describe this with that general region where we describe the bounds for the y in terms of x, a function, a lower bound function, an upper bound function. And I won't sketch all of that, but I'll just jump right to it. If we want to describe this region here, what we're going to have are the points x, y, such that y is less than the negative square root of 25 minus x squared, and less than, so greater than that, and less than the square root of 25 minus x squared. And then x will just vary from negative 5 to 5. But we could calculate the volume here by taking the double integral. For x, it's going to be from negative 5 to 5. And for the y, it's from negative square root of 25 minus x squared, and then square root of 25 minus x squared. Our function here, f of xy, or z equals, is 25 minus x squared minus y squared dy dx. And again, that's all old news. We know about setting this up. I'm going to go fairly quickly through these next two steps, just because, again, I'm not going to evaluate it this way. I just want to show that this is gets very difficult to actually perform this integration if we stay in rectangular coordinates. But let's now first integrate this expression with respect to y. So now I'm going to have just the bounds of negative 5 to 5. This will be 25y minus x squared y, and then this one that has, so these are both constants, that's why I'm doing it that way, but this actually, I'm going to do our normal integration. I'll do 1/3 y cubed, and I'm going to evaluate that at these bounds of the square root of 25 minus x squared, and then the lower bound is negative 25 minus x squared. All right, so the last step, and I'm going to go fairly quickly through this, though it should be fairly obvious what's going on. All I'm going to do is plug this in for y, for my upper bound, and then subtract that, plugging this in. But the fact that these are just opposites of each other is going to end up with this kind of duplicating of each of these terms. But instead of the y's, I'm going to have this expression in terms of x. And so what I'm going to end up with, the integral I would need to calculate, is from negative 5 to 5 of 50 square root of 25 minus x squared minus 2x squared square root of 25 minus x squared, and then minus 2/3, and I'll just write this as 25 minus x squared, the square root cubed, but I'll just write that as the 3/2 dx. And so again, this is where I'm going to stop, and I just want to illustrate that if I wanted to calculate this volume in rectangular coordinates, because of the circular nature of this region that's projected onto this XY plane, this is going to be extremely difficult. Not that we can't do it. We can all do this. Do we want to do 3 terms of trig substitution? Probably not. What I want to do now is step back and talk about, well, then how could we go about calculating this type of volume, but in polar coordinates? All right, in order to develop our method for calculating these double integrals in polar coordinates, I'm going to lean on the work we've already done with rectangular coordinates, and then just make the translation into the polar world. And second of all, if we're going to do this same breaking up these sections as we did in rectangular coordinates, in polar, we're not going to deal with a normal rectangle. We're going to deal with a polar rectangle, which is this shape right here, which is like piece of a circular sector. So this whole thing would be called a circular sector, but we want just this polar rectangle right here. And what we're going to do is to break it up into these smaller little polar rectangles by making these changes in the angle and these changes in the radius. And again, to emphasize, we're breaking this polar rectangle into these little regions by little changes in the theta value and little changes in the r value. So delta r and delta theta instead of delta x and delta y that you'll see in the realization of the double integral. But importantly, just to make sure this is clearly labeled, usually we look at this kth section in the rectangular system as x sub k and y sub k. Again, these stars just mean it's a sample point anywhere within that little section right there. But we're going to describe it in terms of rk and theta k. And importantly, just to kind of talk about it, is that the r sub k right here, the sample point in this little section right here, is the length from the pole or the origin to here. So that whole length right there is the r sub k, and the theta k is the angle that makes that point happen right there. So that's how we're going to look at describing that point. And also, when we think about our deltas, this right here, so this swing between these right here, this is the delta theta, or the change in our angle is that between each of these. And this right here, which is this length from here to here, that would be our delta r. So we get this area of the subsection by a small change in theta over whatever region we're describing, and then this small change in the radius, which is this distance from the pole. And then before we do the real work that we need to do to develop this method of using a double integral in polar coordinates, I want to remind you of the area of a circular sector. Back in trigonometry, probably early on, you saw this definition. And really importantly here, this angle has to be in radians for this to be true. But if you're trying to find the area of a circular sector here, the area is the radius squared times that angle of the opening of that circular sector, and then multiplied by 1/2. And before we go too far, I just want to really clarify what we're doing here. So we're looking to develop a way of calculating the volume under these 3-dimensional surfaces using polar coordinates. What I'm illustrating here, again, just to clarify, is that we're looking at a region on the XY plane. We first looked at these square or rectangular regions that we broke up with these delta Ys and these delta Xs. So we think of the same visual here, but instead we have this polar rectangle, and we're going to describe these little subsections of this polar rectangle in terms of changes in theta and in change in r. All right, so the work that we have to do to convert from rectangular to polar is to first describe the area of the small polar rectangle. So we'll call this the kth polar rectangle in this division of this polar area that we're working with. Again, r sub k star and theta k star are just describing any point on that kth polar rectangle. In order to develop a formula for the area of that polar rectangle, we're going to use the area of a circular sector. Though awkwardly, this itself is not a circular sector. If we, as I have with these dotted lines, continued all the way down, this full shape is a circular sector. And what we're going to do, just to give you a hint of the action, is we're going to think about 2 circular sectors. We have the bigger circular sector here that is bigger than our polar rectangle, and we're going to subtract away the area of this smaller circular sector here. And then in order to develop a formula for this area, we're actually going to make a choice for our sample point on this polar rectangle so that this point right here lies directly in the middle of this polar rectangle in terms of our r value, meaning that the distance from that point to the top here in terms of r is delta r divided by 2. So that distance is delta r divided by 2. And then this distance right here will be delta r divided by 2. Okay, now let's do the work of actually calculating the area of this kth polar rectangle. Importantly to remember is this r sub k star that we've chosen right here. This distance right here from this polar point, the origin to here, is r sub k. And so what I'm going to describe is this full length. And so what that is going to be is r sub k to here plus half of this change in the radius. The radius of the smaller sector right here is going to be that r sub k minus this delta r over 2. So the area of the larger sector will be 1/2 times the radius. The radius here will be this up to here is the r sub k, and then plus this half of the change in the radius, or plus delta r over 2 to get to that full length. So this will look like r sub k star plus delta r divided by 2 squared, and then times the angle, that inner angle right here, but that is simply just delta theta. And then we're going to subtract away the area of the smaller sector, and again, the radius for the smaller sector is that r sub k star, but minus that delta r over 2 to get this length right here. So we have 1/2, and that radius then will be r sub k star minus delta r over 2 squared. And again, our angle though is exactly the same, delta theta. The next step gets a little bit ugly because I need to expand these out. I'm just going to do that quickly. You'll see, as you would guess, since they're very similar, a lot of stuff's going to cancel out for us. All right, and then from that step to that step, all I've done is I first have factored out the 1/2 and the delta theta that we have in both of these terms right here. I've then expanded both of these, and you're very familiar with this. When I expand this, I get this squared in the first term, the last term is this squared, and then I get 2 terms of these 2 things being multiplied together, which you can see here. Again, the conclusion's all we need. I just wanted to show you that this actually is derived from this work right here, and it will make sense what we have in the end, which is a little different than we had with rectangular. But so we have basically the same thing as expanded. The only difference is this middle term, which means that when we do this and subtract these first r sub k star squared terms cancel each other out. These last terms are exactly the same, that negative, so these 2 will cancel out here. Importantly to say is within each of these, this 2 and this 1/2 will cancel out. And so this minus makes that a plus, so I get 2 of these terms right here. So if I still have you following with me, what I have at this point is 1/2 delta theta, and then times, we have 2 of these r sub k star times delta r. And then canceling out this factor of 1/2 and 2 with each other, what I get down to is r sub k star times delta r times delta theta. And then to give this a fully rigorous defense, what I would need to do is develop the Riemann sums that turn into the integrals that we're looking for. But any textbook worth its salt will show all of that work. I just wanted to get to this point right here and emphasize this part is the most important and the one that students will lose or forget about the most, is because this delta A, so this area that we're multiplying by these function values to get this volume, if we're looking at rectangular region, when rectangular coordinates, we have dy times dx. But in this case, we don't just get delta r times delta theta that we might expect. We actually get this value for r at that point on that region right there. So the final version of this, when we make the change from rectangular to polar, will look like this. So we're going to describe our region. Now we'll be describing it in terms of r's and thetas. We need to make the change of variable for the x and y. So we have those relationships up here that I put. This is how you would convert between polar and rectangular. So what we'll actually have is f of not x, we'll have r cosine theta. And for y, we'll have r sine theta. And then we multiply it by our area, these little subinterval areas, these little segments. We have this, which will be r dr d theta. And again, all of that, if you've watched through this work right here, the one emphasis that you want to get because of this little proof right here is the existence of this variable r right here. So not only do you need to make these change of variables from rectangular to polar, in this little area, little bit right here with these differentials, you'll be multiplying by a factor of r. All right, just so we have it in our notes, we have it on the board here. Here's the full description of double integrals over polar regions. We just described these polar rectangular regions. These are regions described by an interval of r values and an interval of theta values right here. It's important to say actually in both these instances is that the difference between the beta and the alpha here, which are these bounds for theta right here, they have to be greater than 0. So they're greater than 0, so beta minus alpha is greater than 0. But less than or equal to 2 pi. So if you're trying to calculate these volumes, for instance, you can't be spinning over 2 pi, or you're going to calculate more or less, I guess in the case, than you should be. But we have those descriptions for this polar rectangle here, so this has a certain radius and certain theta change. We have this right here that we already have stated. I really, again, want to emphasize, don't forget about this. If you forget and think, man, why do we have this factor of r? Rewind and go back to that description of finding the area of a polar rectangle. That's exactly where that comes from. It's why it shows up here. It's the one thing that can kind of frustrate you and throw you off. We haven't done a proof of it, but it follows directly in the same way. If you're looking for a general polar region, as we had in rectangular coordinates, where you're going to describe these kind of regions that aren't constant in terms of y or x, type 1 or type 2. In this case, we're just looking at where we have a definition of our changes in r are based on theta. So as y is usually dependent on x, it's the same in polar. You've probably seen r is usually dependent on theta. That's the description right here. And so the only change in this case is the bounds for our r values come from these functions that are bounding, or these functions defined by theta right here, but exactly the same as you expect, and we calculate it in exactly the same way. And so now we have this, and I'm excited. I mean, all of that work was to hopefully do, and you're waiting for, let's go back to that first example. Let's now calculate it in polar coordinates and see if it's any easier, maybe less trig substitution. All right, so again, we're being asked to find the volume of the solid bound by this paraboloid, z equals 25 minus x squared minus y squared and the xy plane. We looked at this trace on the xy plane, or the region on the xy plane that describes this volume that we're looking at right here. It's a circle of radius 5. But again, just to kind of sketch this, I always like sketching these regions. It can really help you from making mistakes that you might make. But this is a circle of radius 5. And so our job is now to describe this region in terms of these polar coordinates. And really this is the magic and the beauty right here, is how easy this is. So this region we're described in terms of r's and thetas. The set of points that we're looking at are the r values that go from 0 to 5. So r value of 0 all the way up to 5. And the theta values, if we want to create this whole circle right here, that region would just be 0 is less than or equal to theta is less than or equal to 2 pi. So then we have our region that describes our bounds right here. The other thing we need to do is do this change of variables right here. And you might think that you need to plug in r cosine theta or r sine theta directly into the x and y descriptions here and then simplify that, but you actually don't have to go about doing that. The job is, like we've done before in trigonometry, just change this into an equation in terms of r's and thetas. What I mean by that is what I would do actually first here is I'm going to rewrite this a little bit as 25 minus x squared plus y squared. And I'm doing that is because I know that that is the description here of r squared in these change of variables between the rectangular and polar. And so what I get here is z equals 25 minus r squared. So this is my f of xy, or more specifically, this version where I've changed to polar coordinates right here. Now, my double integral for this volume would be 25 minus r squared, and then times r dr d theta. So r dr d theta. This again is just another factor of r. I need to put my bounds in for my r, which is 0 to 5. So I put that on the inside there. And then for my theta is from 0 to 2 pi. And really that's the magic. If you look at this compared to what we had when we started this conversation with all of these square roots, the 25 minus x squared on the square roots, all of that beautiful but time-consuming trig substitution. All of this looks so much easier. This is just a polynomial function in terms of r right here. Our bounds even have zeros as the lower bound, which cuts the work of evaluation in half. But let's do this real fast just to save myself some space that I'm running out here. I want to simplify this first before and then integrate it real fast. This would be 25r minus r cubed. So then what I'm going to do is integrate that with respect to r and then evaluate it from 0 to 5. I'll do that in an extra step. So 0 to 2 pi here. So 25r would be 25 over 2r squared minus, and this would become r to the 4th divided by 4. I'll write it as 1/4 r to the 4th. And we need to evaluate this from 0 to 5, and then we'll be left with an integral in terms of theta. And again, the evaluation of this is pretty dang easy since the fact that I have this 0 as a lower bound. And actually, in fact, when I plug in a 5 here, I'll get 5 squared here, but that's also 5 squared. So this will become 5 to the 4th on top over 2, which is 625. But this is actually going to be 625 also because this is 5 to the 4th, right? So 5 squared times 5 squared, and this is just 5 to the 4th, which are the same. And so what that's going to evaluate into is just the constant of 625 over 2 minus 625 over 4. And when we now need to evaluate that integral or calculate that integral and evaluate it for theta from 0 to 2 pi. And then this arithmetic shouldn't be too much of a stretch. If I'm going to subtract these, I multiply this by 2 numerator and denominator and subtract them. And you can see what I get when I do that. So from 0 to 2 pi, what I'll get is just 625 over 4 d theta. We now integrate that. That is 625 over 4 theta evaluated from 0 to 2 pi. So just plugging the 2 pi in here. And since I'm running room, I won't show that. But again, if I put 2 pi right here and multiply, the 2 and the 4 will cancel. And anyways, what I'll end up getting is 625 over 2 pi. The purpose of this example and this video in general is just to show you that if we have these situations where we're trying to calculate these volumes with this projection on the XY plane that is circular or any other figure that is much easier described in terms of polar coordinates, your life can be much easier if you make that change into polar coordinates from rectangular. And again, this was a super gnarly integral to calculate when we're in terms of rectangular coordinates and was as easy as it gets when we're in polar coordinates. The one thing I again want to emphasize that when we do this is do not forget about this factor of r. If you're sitting there just thinking, where does that factor of r come from? How do I deal with it? Again, it comes from that little example I did in having those 2 circular sectors to find the area of that polar rectangle. How do you deal with it? It's just a factor of r that comes in and plays along with whatever expression or function you have when you've made that change from rectangular to polar coordinates.